Hi everyone, I'm Thomas Wolf from Hugging Face and welcome to my talk at the Data Science Fwdays. So I'm really happy to be here for the second time. I think this is really a great conference. I'm happy it is free this year. I think this is a great idea, and I hope you will enjoy the topic of the day. So the topic will be transfer learning in NLP, and in particular I'll focus on the Hugging Face tools to process text. Okay, so let's start. So first we'll go quickly over what is transfer learning. Okay, a quick introduction, a little bit of history, so everybody's on the same page. So what is transfer learning? So these slides, they are adapted from a very long tutorial. It was a 2 or 3 hours, I think 3 hours tutorial we gave last summer at NACL in Minneapolis. So you can give a look at these slides. There was like 300 slides and hands-on exercise. So if you want more details on the background on what is transfer learning, where it comes from and where it's going, you should really check out this tutorial. But here I'll do a very quick overview. Okay, so this is the traditional learning process that we use in machine learning. So when you have a first task, usually you gather a first data set. These are the green dots you can see here. Okay, you randomly initialize a machine learning system from scratch, and then you train it on your data set. Okay, and when you're faced with a second task, a new task, then usually you redo that. Okay, from scratch, you gather a new data set. Now these are triangles or data points. And you initialize your machine learning model, for instance, your neural network from scratch, and you train it on your data set. And when you're faced with a third task, again, you do the same. So this is very different than the way we do that as human. As human, we kind of rely on all the knowledge we've accumulated over the years, with the various tasks we've been faced with. And we use this knowledge, we use this as the basics. And this let us learn a new task much faster and also get better results when we're faced with a new task. We learn that much faster because we can connect the dots between just a handful of examples. We can connect the dots and say, oh yeah, this reminds me of something I've done earlier, okay? And we can also we can generalize to out-of-domain distribution and things like that because we know a lot of things about how the world works. So transfer learning is one idea to try to apply that in machine learning and in particular in NLP. There are various ways to do transfer learning, but one kind of standard way nowadays is called sequential transfer learning. It involves a sequence of tasks, a sequence of operations, and the first one is called pre-training. Pre-training is a computationally intensive step. During pre-training, we try to use as much data as we can. So we rely a lot on unannotated data, like open domain text that we find, for instance, on the web, or that we can gather from books or from various large-size corpora. And we use that to train a general purpose model. So you probably have heard of many of these names, right? Word2Vec was kind of the first, widely trained on the first models or the first representations that were trained on a very large corpora, very large corpus. And then there was Glovey from Stanford, Skipthought from Milan, Infercent from FAIR, and then the rise of fully pre-trained neural networks with Elmo, ULMFit, GPT, BERT, distilled BERT, and now you know that there are many of them. There's like T5, and you know all these. So all these are general purpose models. They are trained with a general objective, which is usually not the objective we want to maximize or minimize, at least the objective we want to optimize for the tasks that we are faced with. So then there is a second step called adaptation. And during adaptation, we now focus on the task we want to solve, or like we want to tackle. This task can be text classification. For instance, you have a list of tweets and you want to classify if these tweets are positive or negative. It can be word labeling. For instance, you have like newsletter, like newspaper, and you want to label the organization that are mentioned in this newspaper. It can be also question answering. Like you have a Wikipedia and you want to use that to be able to answer question. So the commonality between all these tasks is that usually you need to annotate the data for this task, okay? So this is an expensive process, and it's also a process that can be sometimes very hard if the annotation requires some very deep knowledge of the domain you're in. So usually you have a small corpora here, and you want to leverage the general purpose model to get better performances on a small corpora. For pre-training, there has been a rise of what is called language modeling. Language modeling is the training objective for pre-training. The nice thing about language modeling is that it's very simple. What you try to do is to maximize the probability of the text you have as a pre-training corpus. So you maximize the probability of the text, which can be usually decomposed as the product of the probabilities over the sentences, or the product of the probabilities over the words, or over the subwords if you're splitting words in suffix and prefix. And this is a very simple objective, and the nice thing about it is that you don't have to annotate your text. Your text is basically the annotation itself. So this is what we call self-supervised, okay? Which means you use the input data as the labels. The nice thing is that in many language we have enough text on the internet to learn actually to train a high capacity model in many languages, because we now have this crazy thing called the internet where people post lots and lots of text. Now the quality can be good or bad, and this is also an important question, but at least the quantity is there, which is nice. It's also very versatile. As I said, you can decompose this probability as the products of words or as the products over span of text. So there are many ways you can reformulate, like you can decompose this generic probability, and these many ways give you a different view on your data set. Okay. Now, how does the model look? The architecture, the kind of standard architecture right now is called a transformer. A transformer is an interesting architecture because it's kind of efficient. It's very parallel, so you can compute a lot. You can do a lot of the operation in parallel, which make it very efficient with the current hardware we have. So here is how looks a standard training with what we call a masked language model. So these are like Bert, Roberta, Albert. This is most of the current state-of-the-art models use masked language modeling. So how it works, you take an input sentence. This is how pre-training works. For instance, we have in our corpora, my dog is a good boy, and we'll mask one word. Well, we mask a small percentages of the words, for instance, 15%. Then we use that as input to the model. So we first convert the words in vectors. The way we do that is that we will convert them in integers in a vocabulary, and for each integer, for each word in the vocabulary, we have a vector which is associated. So the inputs embedding are just a mapping from integer to vectors. And here we get vectors. So these vectors, they are not contextualized. Like the dog here, this vector dot is only associated to the word dog and does not depend on the fact that there is my before or there is good after. This is non-contextualized vector. So we want them to be contextualized. We want them to be so that dog is a little bit different. Like the hidden state associated to dog take into account the left and the right context. Okay? So to do that, we use the attention mechanism. The attention mechanism is just a weighted average, basically, of these hidden states. So each token becomes a weighted average of the left and the right hidden states. Then we have a non-linearity. We do that several times. In the transformer, we usually have like between 6 and 20 or 30 or even more layers. And at the end, we still have these vectors. They are always the same dimensionality, but now these vectors, they are contextualized. So this dog vector is specific to the fact that there is my before and mask a good after, okay? And in particular, the mask token now is kind of a specific vector that is adapted to the context. And so we will project back these hidden states on the vocabulary. We basically use here the transpose of the input embeddings. And we use our label, which is the gold answer for the mask token. So here it was is, okay? And this is our training label. So you can see there is kind of a limited signal. Here we just have signal for one word and in the 5 signal, the thing is, if we mask every word, then we have no clue. The model has no clue to try to guess what is the masked word. So we can only mask a few words to give the model enough information with the right and the left context to guess the missing word. So this is a bit annoying. So there is another alternative way to do that, which is to drop the left context to say, okay, we only use to drop the right context and to say, okay, we'll only use the left context. So here you can see that the triangles, they only take care of the left context everywhere. And then we try from each word, given the previous one, so we make the weighted average of the attention with the previous one. For each word, we try to guess the next word. For instance, given my dog is, we try to guess the next word, which is a. So the nice thing here is that now you can see we have a lot of signal. We have signals for each input tokens, but we lost the right context. So our model cannot rely on the ending of the sentence to try to guess the next word, okay? So these are what we call language model, and there are also a lot of them. Mostly OpenAI has been working a lot with what they call the GPT family, the GPT, GPT-2, GPT-3, and so on, but also Salesforce with CTRL, and there are a few things. Okay, so this was pre-training. This is basically how we pre-train, and now we want to adapt our model. So it's pretty simple. Yeah, as I told you, this is a very data efficient step, and it's also give you high performance. So how do you adapt your model for your target test? The first thing is that you will want to remove the pre-training head if you don't use it, okay? So that was for us, that was the down projection from the hidden states down to the vocabulary. And then you will add task-specific elements, which are initialized from scratch, and you want to train them. So they can be very simple, they can be just a linear layer, or they can be very complex. You can have a full LSTM or full transformer initialized from scratch on top of your transformer, and basically using the output of the transformer as contextualized representations, okay? Sometimes it's even more complex. For instance, if you have a task which is structurally different. Here, for instance, we have a translation task, so we have 2 inputs. If we translate for instance, English to Russian, you have an input in English and you also have an input in Russian. And so this is very different because our model was trained with just 1 input. So we need to change this to use 2 inputs. So here you can, there are various ways you can do that, but one way is to duplicate your model, basically. So to finish that, I just give you 2 very different examples of using transfer learning. The first one is on text classification. Let's say we have sentences like here, Jim Henson was a puppeteer, and our task is to classify these sentences as true or false. How does it work? So first, we prepare this input so that it can be used by our model. So our models, they only work on numbers, integers. So we need to convert the sentence. These large-scale models, they are made to be trained on the internet. They are made to be trained on open corpora. Okay, so what we do is that we convert the words. We split the sentence in words. Okay, and if a word is too complex, is too rare, is not common enough, we will split it in suffix and prefix until we know each subpart. So here, for instance, puppeteer is a rare word. It's not in our limited vocabulary. But we know puppet, and we also know the suffix er. So we just split this token in 2, okay? Once all the tokens we have are in the vocabulary, we can convert them in indices. Usually the vocabulary, they are like 50,000 words, something like that, okay? There is kind of a trade-off. A very small vocabulary means you will split a lot the words, but means you will have a small input embedding matrix. But a bigger vocabulary means you will split less the words, but you will have more input word vectors. So you will have more parameters in your model. So once you have only numbers here, you can use the transformer basically. So this is what we saw on a few slides ago. This is the attention here, and the output is a vector for each input token, okay? So we have a vector here, which is the contextualized version of Jim. And here another vector, the contextualized version of was, okay? And this is all pre-trained. And now comes the part that is trained during the second step of transfer learning. And this is a classifier model. So it can be very simple. For instance, in our text classification here, we can just actually pool this representation. For instance, we can do max pooling or average pooling, so we get just one vector. And then we just have a down projection with a linear layer from the dimensionality here, which is 4. It's obviously just an example, but usually which is a few hundreds. So from this input dimensionality down to the number of classes. So we can have just a linear projection from 4 to 2. Okay, and we train it on our target task. So here we assume we have a small training data set with some labels for sentences, and we can use that with a softmax to train a model. So here is an example. Track 6 is a 6-class classification, 6-class classification data set. And here you can see two interesting things. So this was during the tutorial. I told you we did this tutorial last summer, so you can check the full code of the hands-on exercise. It's very simple, and you can see two things. The first one is that just after one epoch, the error rate on this target task is already down to less than 10%. So we already have an over 90% accuracy. So it's very data efficient. Just one epoch, and the dataset is very small. It's 2,500 examples. So it's very small in deep learning terms. And the second thing you can see is that the final error rate is 3.6 after 3 epochs, and it's close to basically the state of the art at that time. Okay, so it works really well. Now here is a second example, very different. It's language generation. Here we take a dialogue generation task where we have a knowledge base, we have a persona of our chatbot, and we have a history, the interaction with a user. The user say hi, the bot reply, hello, how are you today? And then the user say, I'm good, thank you, how are you? And the chatbot is expected to generate the reply, okay? So this is one case where we have a lot of different type of inputs. We have this knowledge base, we have a history, we have a utterance, and we have the beginning of the reply if we are building the reply word by word. So one question is, how do we modify our model to handle these various type of inputs? There are many ways you can do that. You can duplicate the model, you can make it an encoder and decoder, or you can concatenate all these inputs to build a single input for the model and just generate the reply as the continuation of the input. So we have a paper in ACL last year where we kind of compared these two variants. It's quite interesting. Here is one example now from 2 years ago competition. That was, I think, the first cases of using transfer learning for dialogue generation for chatbot. That was actually the first thing we did with Hugging Face. We were using GPT-1, which was the only large-scale pre-trained model at that time. BERT was not out yet. And as you can see, we kind of get the best result in the competition on a various number of metrics. Okay, in this second part, we'll talk about the trends and the limits of transfer learning in NLP. So one trend you may have seen is that the models are getting bigger and bigger. So for a long time, it was already just a few 100 million parameters. That was already quite big when BERT was out. And then OpenAI moved above the billion parameter limit. And then a lot of people followed with NVIDIA training an 8 billion Megatron language model. Then Google training the T5 with 11 billion. Recently, you've probably heard about GPT-3, which is 175 billion parameters. And even more recently, Google published a paper on the G-shard technique, which trained 600 billion parameters, and I think they even tried a trillion parameter model in this. So this is a model translation model. This is a very nice paper. You should check this out. So this is one trend. So over 1 billion parameter is now the norm if you want to reach the SOTA, the state of the art on many benchmarks. This is a problem, all right? This is a problem because the competition is quite narrow now. If you check the leaderboard of Glue, you basically only see Google, Baidu, Facebook, and just only big teams because academia doesn't have the resource, doesn't have the compute, doesn't have the compute power to train such big models. also have a strong environmental cost, so this is a problem. And then there's also this question of, is bigger better scientific research program? Okay, as François Solé stated that, I mean, training either bigger ConvNet on LSTM on ever bigger dataset get us closer to strong AI, in the same sense that building taller towers get us closer to the moon. Okay, you can build a very high skyscraper, but you still like, this is not the way you will reach the moon in any way, in any case, right? So an alternative is to reduce the size of the model. We've been working on that a lot at Hugging Face. In particular, Victorson has been investigating distillation first. With the distilled bird model last year, you can basically reduce the size of bird by half and get almost the same performances. And this year we've worked a lot on pruning, which is also a very interesting way to reduce the size of the model. Quantization is also interesting. You can convert these float numbers to integers, and this is also something you kind of want to do. So there are all these ways to reduce the size. Now another question is also the inductive bias question, the generalization problem. Models are brittle, they fail when text is modified, even when the meaning is preserved, and they are spurious. You memorize artifacts and biases instead of truly learning. So here are two good examples of brittleness and spuriousness. Brittleness, I think the best example was this first paper by Robin Jay and Percy Liang in 2017, where they added a random sentence at the end of Squad. Squad is question answering, that's it, kind of famous, where they have like, you have a paragraph from Wikipedia and you're asking a question on this paragraph, and the model is supposed to extract the answer. And the model was totally lost when you had a random sentence, when you add a random sentence at the end here, which is brittleness. Okay, this fell in an unexpected way. You don't really expect that as a human, so it's very hard to detect. It's very hard to anticipate. Spuriousness is a bit different. Spuriousness, the idea is that the model will rely on the easiest signal. So if you have, for instance, this is a MNLI, so it's an entailment task. So you have two sentences here. For instance, the doctor was paid by the actor. And you have a second sentence, the doctor paid the actor. And you're supposed to choose between three classes. You're supposed to choose if the model is, if the first sentence entails the second, if the first and the second sentence contradict each other, or if they are neutral, they have no strong relationship. And here you see that there is this one, they contradict each other, right? The doctor was paid by the actor, or the doctor paid the actor. They means the opposite, okay? In the first one, the actor paid. In the second one, the doctor paid. But because they have a lot of lexical overlap, and because in the training dataset, lexical overlap usually means entailment, the model will think they entail each other, okay? The second sentence is entailed by the first. So this is what we call, this lexical overlap is what we call a weak heuristic that the model shouldn't use. The model should try to get the meaning and not use just this surface form matching. But because it's easier, and because it's also a bias in the training dataset, the model will use these heuristics, and then it will fail, of course, when the heuristic doesn't work, because it's a shortcut that we don't want the model to take, but they like to take these shortcuts. And now we have more general shortcomings of language modeling in general. You need grounded representation. There's a limit to what you can learn by text only, and this is usually called the human reporting bias. There is an interesting paper by Gordon and Ben van Derm, which is that we don't state the obvious. Okay, we don't state the color of everything that people know. We don't say that sheep are white. We don't say that rooms have windows, because everybody kind of expect that. We only state stuff when they are not obvious, when they are different from the usual. And this is a problem, because it means there are stuff you just can't get from the text. They're not just almost never written. So the way to overcome this is like to use database, for instance, or to use other modality like images, or to use a human in the loop approach. Okay. And then there is also the problem of meta-learning and continual learning in particular. Like all these models, they are static, and we would like them to evolve. We would like them to be able to learn new knowledge without having to retrain a model. Like GPT-3 costed several $million to be trained, and we want it to be able to evolve in the future without having to without having to retrain it from scratch or to like fine-tune it in kind of complex way, okay? So this is a very open problem. Now let's talk a little bit about Hugging Face and what we do at Hugging Face. Hugging Face, we try to democratize NLP. We try to make the recent breakthrough of NLP accessible to everyone, and in particular everyone in the research and the practitioner communities. We like a lot intelligence or artificial intelligence as creativity, interaction. We like a lot the fact that model can generate text, can interact with human, can be not just a way to make sense of data, but a way to generate new data in a creative way. That's something we like a lot. So we like a lot NLG, which is called natural language generation, but we also like natural language understanding, and we think both goes hands in hands. We started with a chatbot product, and while we were developing this chatbot product, that was used actually by a lot of users. It was a game that was used by many users, and while we were developing this, we started to open source a few tools we were using. And these tools, they just catch up so much interest from the community that very quickly we were just spending all our time developing these tools. So we're now trying to focus on this only, which means sharing a lot. So it means sharing knowledge, sharing code, sharing data. This is all we mean by democratizing NLP. So sharing knowledge is, for instance, what I'm doing here today. I'm very happy to share knowledge with you. Sharing code and model is what we are doing on our open source repository on GitHub. This is very important for us. We want to break the barrier. We want to make it very easy for people to access these models, very easy for people to use them as baseline, very easy for people to investigate what's happening in these models, to understand how they behave and why they behave the way they behave. We think this is also important in terms of ethics and bias. Being able to understand the limits of this model is something we really want to push forward. And so this is how we do that, by trying to break all the barriers between researchers, between practitioners, between PyTorch, between TensorFlow. We think there's a lot of artificial barriers that are slowing down the field, and that kind of make it harder to build a science in the field. Okay, so we have a few libraries now out. Let me go through them very quickly. Transformers library is one library you might likely know if you're working in NLP. It's a library to access models, pre-trained models. So we have a lot of pre-trained models now in a lot of languages, like a lot more than 100 languages. We have a lot more than 30 pre-trained models as well. This is a little bit old. I should update this. And the idea is that you can access all these pre-trained models in just one line very easily. So you can compare them together, you can access the internals of these models, you can try to build new models on top of them. So all this is what we want to do. So this you can check on the repository. It's very easy to use. A lot of these things are made to be one-liner while still letting you access what's inside. Okay, we want to keep this very open, very transparent. So the best is check out the GitHub repository to have all the information, documentation, tutorial. Now that we have also focused on one bottleneck we have identified for NLP models, which is called tokenization. This is the step we saw at the beginning, which is the step of converting a string in a list of tokens that the model can use as inputs. This can be very slow in Python because Python doesn't like loops, basically. So we've built a low-level library called tokenizers, which is built in Rust. Rust is a very fast, low-level language. And this library takes care of doing the most common conversion from string to token, doing byte pair encoding, byte level, byte pair encoding, word pieces, sentence piece. All this way to split a string in a list of tokens is handled by the library. It's really fast. It can encode like 1 gigabyte in just a few tenths of seconds. And it's used in the Transformers library by what we call the fast tokenizers. So here also, I won't spend a lot of time, but just send you back to how to use it in Python, in Node.js, or in Rust, and check out the repository for more details, and you will see how to use it. And now the last library we open source just a few months ago now, just like 3 months ago maybe. It's called NLP. It's a dataset on matrix library. It will soon be called datasets. because it's actually more generic than NLP, where we start to have multimodal thing. And here the idea was to take care of the beginning and the end of the data processing pipeline. So we started with the prediction part, the transformers model. Then we did a focus on the tokenization part to optimize this part, okay? How you prepare from string to the integers and then to the prediction. And now we think there is still a lot of things that can be improved on the data access, on the data sharing, on the data processing part, and also on the metrics evaluation, okay? So how do you prepare the data for your model in an efficient and very simple way? How do you access all the data sets that are public and available in a very simple way as well, a bit like what we did for the models? And also at the end, once you've trained your model, how can you evaluate your model in a reproducible way, in a very reliable way, okay? So this library take care of these both ends, okay? It's a very lightweight library, it's simple to extend, and it also relies on a very fast low-level thing, which is called low-level serialization protocol, which is Apache Arrow, which is very efficient. And in particular, it can really work very well on super large data set, like using Wikipedia, which is 18 gigabytes. It's there is a very smart way to do memory mapping with zero cost serialization on drive, which means take just 9 megabytes of RAM when you load Wikipedia, and you can iterate at full speed on the dataset, like 1 or 2 gigabytes per second. So it's really, really fast. You have a smart caching. Once you've processed your data, you never have to reprocess it. All this is made to be very smart, very fast, and very simple to use. There is currently a little over 150 dataset, but it's growing quite quickly because the community is already adding a lot of dataset and metrics. And we have like 15 metrics, something like that. So you have all these kind of strange and difficult to implement metrics in NLP, like Rouge, like Sacre Bleu, like Meteor, like, yeah. And also more recent metrics using neural network, like Blurt, and yeah, like a lot of things like this. We also have an online viewer that you can use to explore the dataset, so you can check it out at Hugging Face NLP. So now in the last part, I want to show you a little bit a preview of what you can do by combining all these libraries together. Okay, this is what I've been working a lot over the summer. So let me show you a little bit. Okay, this is this Collab. Yeah, I won't run it right now, but this will be basically on the master and then the next release of Transformer around the end of August, so probably in 2 weeks. And this shows you how you can use all these tools to make a very efficient and reproducible fine-tuning of the models. So let's say we want to do a very standard fine-tuning of BERT and glue on the sub-dataset is MRPC, which is the Microsoft Research Paraphrase Corpus. Okay, so the task here is paraphrase detection, paraphrase classification. So you import NLP in Transformer. We'll do a hyperparameter search to get good results with Optuna, which is an interesting hyperparameter optimization library. And basically, you start by loading the tokenizer. You should remember, this is the thing that converts from string to list of token. We load the dataset and we load the matrix that's associated to MRPC, okay? In our case, you'll see. So this just download everything and process, and then you can start to explore the datasets. So our dataset is just a dictionary. Okay, there is a few splits. There is a test, a train, a validation splits. And each split is a dataset. This is just a container, a standard Python container. Okay, so you can access the element by indexing. Like we can take dataset train, the first element of dataset train, and you can see that the first element of dataset train is a dictionary with a few columns. Okay, so each sample in the dataset has an index, a label, label 1, a sentence, the first and the second sentence. Okay, so the goal of this task is to detect if the first and the second sentences are paraphrase of each other. And all these are typed, so you can access the feature. If you do dataset.train.features, you can access the feature, and you can see that these are typed. The sentences are strings, the ID is just an integer, and the label is a class label, so you have an associated name. Okay, you can see basically 0 means not equivalent, and 1 means equivalent. And you can use this feature to convert from the class names to the class integers. Now to tokenize, we use the tokenizer. We have an uncode method that tokenizes the two sentences together in one single input. we truncate them to the max length of the model. So when we don't specify specific max length, it will use the default max length of the model. And we just map this method on the whole dataset. So this basically tokenizes the dataset. Then we have a little bit to rename one column. We have a label column, but the model in the transformers, they use labels instead of labels. So we rename this column. And when we give a look at the dataset, how it looks after tokenization, we just access the first element of the train dataset. You can see that it has now the list of integers as inputs, okay? And the features has evolved. So the features now, they have additional columns. You have like attention mask, which is a sequence of integers, input IDs, which is a sequence of integers, and token type IDs. So these are all added by the tokenizer of transformers, and these are just the standard expected inputs for the models. Now when we want to train to use the data to train the model, we don't really want to use the string inputs, okay? Our model just care about the integers input. So we can add what we call the format to the dataset, which will filter and only output the columns we want to train our model. So we still keep the string column, they can be useful later, but we don't want to output them as inputs for our model. So we set the format to say, okay, we only need the columns attention, mask, input ID, token type ID, and labels. And when you access the first element of the training split, you see we only have integers. So we can use that as an input to our model. So to use that, we'll just put this data set in a PyTorch data loader and just use this as input to the models. So now we import Torch, and this is our simple train method that train for one epoch. We put a model in train mode, we put the model on device, and we iterate over data loader, put the batch on the device. Well, this is very simple. The most maybe a thing that you're not very used to is gradient accumulation, so we can use large batch on the single GPU of Collab. And then we also do an evaluation loop using our metric. So we just output prediction. Well, we go through the model with each batch of our evaluation data loader. We output prediction, which has just the argmax, the highest logits, and then we just add this batch to our matrix, and at the end we compute the metric. Now we want to do a simple hyperparameter search to be sure that we get a good result. So we use Optuna. Optuna is pretty simple. You just define an objective function that will return the thing that you want to maximize. So in our case, we just maximize the sum of all the metrics we were computing during the evaluation. And this objective method takes as input a trial object that you can use to sample the hyperparameter. So here we sample the learning rate, we sample the number of epoch, we sample whether we correct the bias in Adam, a few things, the seed, okay, the schedule. So we sample a few hyperparameters. We check if we need to use gradient accumulation, if the batch size is too big for the Collab GPU. We've defined a max batch size on the GPU. And then we have a simple collate function. If you are familiar to PyTorch, you know that this is used to gather a series of examples in a batch. So in our case, the only specific thing we do is that when we have a series of examples, we all pad them together to the longest sentence in the batch, okay? And we also return PyTorch tensors, so it's ready for the inputs. So this is our collate function that we use in the data loader. And now we're ready. So we define the seed, because this is an hyperparameter. We initialize the model inside the seed, inside the seed, yeah, sorry. We build the data loader from our data set. We build the optimizer with all the thing with all the upper parameter, the learning rate and things like that. And now we can train the model for the number of epoch. Okay, so we use the train method that we've defined here, that return the eval metrics. So the eval metrics is a dictionary. There can be several metrics. So what we do is that we just sum all these metrics together, and we say, okay, this is the thing we want to optimize. In our case, I think for MRPC, it's F1 and accuracy. These are the two metrics that are standard for this subpart of Glue. So we just sum the F1 and the accuracy, and we say, okay, this is the thing we want to optimize for hyperparameter search. Now, one thing about recent hyperparameter libraries like Optina Array is that you can do pruning during the hyperparameter search if the trial looks not interesting. Okay, so we start a study.optimize. We create a new study. We want to maximize the metrics, and we run it for like 30 minutes. You can see it does another number of trials, and we can print a few summaries. It did like 22 trials, pruned half of it. That were just not looking good, and it gives you the best hyperparameters. And you can have also the importance. You can see that the seed is very important, the random initialization, the batch size is also an important hyperparameter, and the learning rate schedule is less important than the other. And now we can rerun the best trial. Just use a study.best trial. We build a fixed trial. Fixed trial means that each time we sample just the version that were the hyperparameter that was saved in this best trial. And we can run it again to save, for instance, the model at the end, okay? And you can see the metrics. We get an accuracy of 0.86, which is pretty good, and F1 0.9. So yeah, that was working pretty nice. And as you can see, it's pretty simple, okay? This is the hyperparameter search, to remind you. And this is the full training loop, so it's quite simple. Okay, and this basically concludes what I wanted to show you today, and I'm happy to take a few questions if we have some time. Thanks a lot.
So, hey Thomas.
Hey, yes.
Thank you very much for your talk.
Yes, I'd like to say that it was totally awesome, clear explanation of transfer learning and transformers. I even don't know what kind of specific questions I could ask, but while we are waiting for questions...
Can I interrupt you for a sec?
Yes.
Thank you. I just wanted to say that, Thomas, we are so happy to see you online because, you know, last year you were in Kiev and we were so excited that you made it to our conference, and we really hope to see you again this year, but, you know, the pandemic situation, all the stuff. We still hope to see you in person maybe next year or where it is possible. So thank you for joining us online.
We have first question. So I'm reading it. Are you planning to add Grover to Transformers library?
Grover? Oh yeah, that's right, Grover. Oh, that's a good point. We could add it. Yeah, I kind of forgot about this one. It's a good one. Yeah, we should add it. Can the one who posed the question open an issue so we keep that in mind? I think I just forgot about this model. There are so many models, but this one is a nice one.
Thank you. Our listeners, they hear with some delayed, around 2 minutes, so maybe they then can ask some more questions. And while we are waiting for some more questions, I can ask you my general one. So, what do you think? What are the first steps in research on natural language processing field? In general, maybe something about transfer learning. Maybe you know about some papers that are work in progress now, and they will be published soon.
Do you mean the current step at Hugging Face, or do you mean the first step for somebody who wants to start to work in NLP?
No, I'm talking about researchers. So, do you know about some interesting researches that are going on now?
Oh, now, oh yeah. Yeah, so one thing I like a lot at Hugging Face is knowledge-based model, which are model with one part which is a knowledge base. So there have been these are sometimes called non-parametric model because one part of the model is not in the weights, one part of the model is stored as a database. So there have been a few recent examples like KNN language model or Marge or the Realm. Realm is a model by Google that was actually open source yesterday. It's the successor to Orca. We think at Hugging Face, where I think at least that these models are really interesting. The nice thing is that they can evolve in time. So for now, they know, for instance, that COVID is there, but next year you can change the database, so they know that hopefully COVID is gone. So you can make them evolve very easily, and they can be very big without costing too much. So they are very promising. We've been working a lot on this model at Hugging Face, and I hope there will be some part of the future of NLP, rather than just this very big GPT-3 type of model, which are very difficult to handle for many people. So this is one thing which is important. We work a lot on that. And another thing is also to improve the practice in kind of bias investigation. That was something we want to work more, like how can we make our models like better understand their failures and predict where they will fail for bias reason. But yeah, there are many other things. We also work on efficiency, pruning, sparse model. We will probably soon open source a library for simple sparse model training in PyTorch. So yeah, there's a lot of things, but yeah.
Thank you for your answer. And I see that we have another question. How do you long? Wait, I'm sorry. How do you think? How long till NLP models can pass Turing test?
Oh yeah, that's a good question, right? I think we're there yet, right? I think the recent kind of very large-scale language model, they very likely can pass the Turing test. Can be the Mina chatbot by Google, like all the recent wave of large-scale chatbot. GPT-3 can also very likely pass the Turing test. I think what we've seen also recently, and there was an interesting discussion on Twitter, maybe I can post it here, is that the Turing test is probably a bad test because it's just about mimicking human. It's not really about creating something new and like something more interesting, more different than what exists. It's just about copying a human. So there is actually a limit. We've adopted the Turing test as this idea of the AGI detector, but it's actually not the best test for that. It's quite easy in some way to overcome. So yeah, there are better tests for that than the Turing test, but I think we're there yet. Today, we already, I'm pretty sure a lot of current language models could pass the Turing test.
Okay, thank you. And we have another question. So, can you share some good examples of named entity recognition with transformers and some fine-tuning?
Oh, where is this question? It's not in the chat. Oh, maybe. Oh yeah. Can you say it again? Sorry, during the beginning.
Yeah, I can say it again. Do we have some sound issues?
No, we don't.
Oh no. Okay, I get it. Yeah, I get it. Yeah, a good example of name entity recognition with transformers and some fine tuning. Yeah, so this is something we are working on actually right now, and until the end of August, I will work on making a new series of tutorials that should be better, and name entity recognition and token classification is one part we can make the tutorials a lot better. So I think by example, they would like a code example, right? Yeah. So we have one. It kind of depend on the language as well. So we have good data set for this in English, Arabic, and Chinese. But if you're looking in other languages, it's not always easy to get a good data set to train your model. But I can post some point. Let me post some pointers on Telegram quickly on that. Gosh, man. Basically, Roberta is pretty good model to that. Yep. Okay. Yeah, let me post this. And keep posing questions. In the meantime, I'm trying to get the link so I can post them right now before I forget about that. Okay. Name entity recognition, this one.
By the way, if you can't find this link for now, you can post it to us later, and we can repost it to our chat.
Yes, we have a chat in Telegram.
Yeah.
If you're not there, we can do this for you. It's no problem.
Oh yeah, probably it's good because I see that Telegram doesn't want me to post external links.
Oh,
Okay.
just chatbot deleted your message.
Yeah.
You know, we have the chatbots for people who post some spam, but you are like the newbie for this chat, and this is why he thought that you're a bot.
Yeah.
So just send it to me or somebody who are you in touch in Telegram, and we will just post it.
Yeah.
Okay, I send it to you.
Okay.
There you go.
Next question
Yep.
is, so what do you think about future of models like reformer or long former?
Yeah, that's a good question. I think these models are very interesting. We have in our place, it's mostly Patrick. Patrick is working a lot on this model. He has implemented both of them, and they work really well. We also have now benchmark for memory and speed, and they are really very efficient. Also, the link former also is very nice. I think this model will be probably just the standard toolbox in the future. I see them as just being, they are not breakthrough. They are just mostly improving what is already there, but they are making this much more efficient. So, well, one limit though is that you mostly want to use them on long type of inputs. So if your day-to-day work is just with short text, like tweets, things like that, you probably just don't want to use this model. They're mostly interesting if you want to do like summarization or like question answering on big data sets, like closed form question answering. So they are mostly for some use case, but for this use case, they are very like the natural way you should go.
Okay.
A bit like sparse attention. Like I also expect us to use this a lot more in the future.
Mm-hmm. And we have another question. So, what are the spheres that can be revolutionized and tremendously change our life with good NLP models?
Oh yeah, that's a big question, right? I think sometimes we don't understand how much natural language is just at the core of everything we do, like the internet. If you have a small child that can't read, you can see that there is just so much you just can't access, and once you're reading, you just access the whole internet. All our knowledge is stored like that. All the way we chat, we interact with computer. We use a little bit of photo and video, but like 90% of this is just natural language processing. So basically, I can see everything being kind of changed by the fact that we can now, models can start to understand depending on how you define it, but can start to process text a lot better than they used to. In particular for low language, like usually it's kind of difficult to have good, like if you need to define a new data set with linguists in a low language resource, it's quite hard. But if the only requirement is to gather a huge data set, like a bunch of web page in one low resource, or like a small language, it's a lot easier. So it will also make it easier to use NLP in many languages. I can see a rise of multilinguality. So yeah, in a lot of things. Overall, I don't think this will replace job or thing like that, but this will most likely be used as a help for people in pretty much every field that use text. So legal is something that is very strong. For instance, like currently searching in legal database is very difficult. You can improve that a lot with NLP. Search is probably the most impactful area in general, just searching in some open corpus, something that can be very difficult and can be really changed by NLP and question answering, things like that.
Okay, thank you. I see that we don't have any more questions, right?
Oh, we are out of questions.
Yeah, it looks so, but I can ask some
last question.
last question.
Yes, because we're out of time.
From my side, yes, because we are out of time. You said that there is a problem, I wrote it called brittleness, so that model change its prediction when we change some words or some sentences in input text, but this input text has the same meaning, but model makes other prediction. Can we avoid such kind of problems with making some data augmentation for training data sets? Do you know some good examples or techniques for text data augmentation?
Yeah, that's a good question. Yeah, I think this is thought to be not possible to do mostly, but now with better language generation, like technique, we can do some data augmentation. Now there is a race, obviously, it's a bit like a GAN because you're augmenting the data with a language model, so it's something that you generated yourself. So the model that you retrain is competing with some other model. But yeah, there is a lot of things on this thing, like doing it's related to adversarial training, where you try to find the example where your model like fail, and you can also generate, now you can start to generate adversarial example, and you can also use them to train your model on it. But yeah, I think in general, I think there is a limit to what you can do with this automatic data augmentation stuff, just because you're using a neural network also to generate. So yeah, you cannot solve everything. But like back translation was very useful for matching translation. So these are the similar idea. We can do some noisy augmentation with this model that works. There's a few library. Let me see. I'll see if I can post a few links as well. There was a recent work called Text Attack, which is a generic library for adversarial attack on models, which generate this type of thing.
I think this is it. Thank you. I just see a few more questions. Thomas, if it is not hard for you to just write in text your answers.
Yeah, sure. Oh yes.
If it's
now
not
I can
huge that I'm asking. Because we really need to wrap it up to the end, and we are having another activity which you are participating in too. So Thomas will be on discussion like in 10 minutes.
Okay, I still think I cannot send links though, but yeah.
You sent it, we see it, and then the bot yelled at you. But
okay, but you can still see, even if the bot yelled at me.
Yeah, it yells, but it allows you to post.
Okay, that's right. Okay, let's keep doing that then. Okay,
such
nice.
Tricky bot.
Okay. Okay, then talk to you later for the panel.
Okay, thank you, Thomas, again. See you in Zoom in 5 or 10 minutes, something like this. Thank you again so much.
Good. Yeah. Okay, bye-bye.
See ya.